In this MindBite, we talk about hardware to achieve angle modulation, both frequency and phase modulation. So we talk about narrowband FM. Now usually this is only produced as a halfway house to producing wideband FM. We also talk about demodulation via several different routes. Firstly, differentiation, which turns a wideband FM signal into an amplitude modulated signal, and then you can use all the techniques we used for amplitude modulation, or these cunning things called phase locked loops. This is our expression for a narrowband angle modulated signal, having the two parts, the carrier part and the amplitude modulated part. Remember, this is an approximation when our message phi is small. This is a block diagram that directly implements the equation above. So we have a message signal coming in here, an integrator, which is necessary if we're going to produce a frequency modulated signal rather than a phase modulated signal. And here we have a multiplier, which multiplies a sine carrier oscillation with the phi of t to give us this term on the right, the amplitude modulated signal. That part comes along here and is summed with a cos at the carrier frequency, which gives you this term here. So the output is the carrier term, which comes this way, minus the amplitude modulated term, which comes this way. So this is a direct implementation of narrowband FM. So how do you produce wideband FM from narrowband FM? Remember, the only difference is the size of the modulating factor. So is there a way we can increase the size of a modulating factor in a narrowband FM signal? And there is. This first equation is a narrowband FM signal at half the carrier frequency, and it has a modulating factor that is half the modulating factor we're aiming for in our wideband FM signal. What happens if you square this, i.e. you multiply it by itself? Right, here's our narrowband FM signal squared. You remember that cos squared and cos of 2 theta are related by our formula for cos 2 theta. So we can write out our squared term in terms of a cos at twice the angle. Now if we double this angle, then the carrier frequency doubles and the modulating factor doubles. And so by squaring the narrowband FM signal, we've doubled the frequency and we've doubled the modulating factor. So this is how it's implemented in hardware. You have your message signal, which is a narrowband FM signal, and you take 2 copies of that output and feed them into a multiplier. So the multiplier squares the narrowband FM signal. The output has a low frequency component, which is this component around DC, which is easy to filter away with just a capacitor, and a high frequency component, which is the wideband FM that we're after. There are also direct methods of producing wideband FM signals. There are very cunning pieces of hardware called voltage controlled oscillators, and these oscillate at a frequency proportional to an input. Sometimes the frequency is proportional to the derivative of the input. It depends on the exact voltage controlled oscillator that you buy. In this case, if we produce our phi of t by putting our message signal through an integrator, for instance, or we just use our message signal directly, we add a voltage proportional to our carrier frequency and input that into a voltage controlled oscillator, then the output is our wideband FM signal. Now, the problem here is getting a voltage controlled oscillator that will oscillate at a sufficiently high frequency for us to use as a carrier frequency. However, it can be done, and you could always upshift afterwards. Demodulation of FM signals. One of the more common methods is to differentiate your wideband FM signal. Here we have a wideband FM signal. Remember, we know it's FM because the phase angle is proportional to the integral of our message signal. What happens if we differentiate this? Well, the constant AC is just going to stay a constant. The cos of all this stuff turns into the minus sine of all this stuff. And then using the chain rule, we have to differentiate all this stuff inside the bracket. So we have to differentiate this angle. So if you differentiate the carrier frequency times time, you just get the carrier frequency. If you differentiate a constant times an integral, you just get a constant times the message signal. Remember, differentiation undoes integration. And so we get this term, which is the modulating factor times our message signal. Now this thing, this whole expression here, looks a lot like an amplitude modulated signal. We have an amplitude that's proportional to the message signal, and then we have a carrier wave oscillation, although in this case our carrier wave isn't at a fixed frequency. It's at a frequency which varies with the message signal. But that doesn't matter. If you use a non-coherent demodulator, one that just joins the peaks of your signal, then it can demodulate this, and it doesn't really care that the frequency is changing slightly as you go along. So by putting this signal through an envelope detector, you can extract the amplitude as a function of time and hence get your message signal back again. This is a diagram of what this could look like. We have an information signal that goes through a smooth up and down. This is our FM signal, so low frequencies where the information signal is low, and high frequency where the information signal is high. Now if you differentiate this, then you get a high amplitude where the frequency is high, and a low amplitude where the frequency is low. So you can see that the envelope of this signal looks a lot like our information signal. And this is very similar to an AM signal, except that the frequency when the signal is high is higher than the frequency where the amplitude is low. But an envelope detector that just tracks along these peaks, it doesn't care about that. A block diagram of hardware to demodulate a wideband FM signal is to put it through a hardware differentiator that takes us from graph B to graph C, and then our AM signal that's produced can go through an envelope detector, and that would yield the envelope, which is our information signal. How do you make a differentiator? Differentiation is hard. You can fill whole blackboards doing differentiation. How do you produce a piece of hardware that's going to do it? Unfortunately, it's much easier than doing it on a whiteboard. A differentiator is a linear circuit of a transfer function which is just proportional to frequency. Remember that differentiation in the frequency domain means multiplying by j omega. Now there's all sorts of devices that will do that over narrow frequency ranges. We only need it to be a differentiator over a very narrow range of frequencies which are in our communications channel across the bandwidth of our modulated signal. So for instance, if this is our carrier frequency and these dotted lines indicate our bandwidth, then we only need a circuit which has a transfer function which is mostly linear in this range. Doesn't matter what it does out here, doesn't matter what it does out there. So a bandpass filter, for instance, with a characteristic like this is sufficiently linear over this range to be used as a differentiator. Therefore, it's relatively easy to build a hardware differentiator as long as you're only looking at a narrow range of frequencies. Another hardware method for differentiation is the use of a phase-locked loop. Now, a phase-locked loop uses a voltage-controlled oscillator in a feedback system. Now the system is such that the output here, which is your feedback signal, is proportional to your message signal if the input is a frequency modulated signal. So just the overview of how this works. This multiplier multiplies these two oscillations together, and so the output has both the sum frequency and the difference frequency. Now the sum frequency is going to be at twice the carrier frequency, and so this low pass filter is going to get rid of that, so I'm not interested in that. The difference frequency has the carrier frequency here minus the carrier frequency there, which gives you nothing. So the output here is an oscillation with the phase angle, which is just the difference between the feedback phase angle here and the input phase angle here. Now that's at a very low frequency, so that's going to get past this low pass filter, and that's going to turn into the feedback, which will change the frequency of oscillation here to try and reduce the difference between this phase and the feedback phase. Now that means that this feedback signal is close to the time derivative of this input phase here, because this feedback phase lags it slightly. So you're looking at the difference between the phase now and the phase a short time ago, which is essentially a time derivative. And so if this is the time derivative of phi of t, then it's the message signal when the input is a frequency modulated signal. So here's that overview explanation in terms of squiggles. We have the multiplier multiplying the cos and the sine together, and that gives you two terms at the output, one of them at the sum frequency, which is twice the carrier frequency and the two phases, and one at the difference, which doesn't have any carrier frequency in it, it's just the difference in the two phases. Low pass filter gets rid of this term, and so the output here is just the sine of the difference in the phases. Now, using our Taylor-Maclaurin expansion, this is going to be a small angle, so the sine of this angle is approximately just the angle. And so it's the difference in the two phases, which over a short time step is a good approximation to the derivative of the input phase, phi. This difference comes back and is fed into our voltage controlled oscillator. Now this voltage controlled oscillator takes the integral of the input. If it doesn't, you can put a little op-amp integrator in front of it. The feedback signal is designed so it forces the voltage controlled oscillator to try and track the input at the multiplier here. So when the circuit is up and running, then the output is our message signal if the input is a frequency modulated signal, either wideband or narrowband, doesn't matter. These phase lock loops are also used in receivers to track the carrier frequency when using superheterodyne AM demodulation. Narrowband FM is not often broadcast, but is often produced on the way to generating wideband FM. It may be you have to square it once, or maybe even twice to get up to the carrier frequency, and each time you square it you double the modulating factor. Voltage controlled oscillators can produce wideband FM directly. Differentiation of a wideband FM signal yields an AM amplitude modulated signal, but with a variable frequency carrier. But an envelope detector doesn't care about that, and it will give you your message signal back again. A voltage controlled oscillator in a feedback loop is called a phase locked loop, and it can be used to demodulate a wideband FM signal, and they're also built into receivers to track the carrier for superheterodyne demodulation of an amplitude modulated signal. And that's the end of our section on analog modulation.